Hi everyone, let's get started. This is our lecture on projectile motion, horizontal launches. So that would be an object shot with an initial horizontal velocity, but no initial vertical velocity. All right, so in order to get started, we need to just very quickly recap two-dimensional motion, or what we refer to as projectile motion. Whenever you go ahead and throw an object or launch an object into the air, our overall velocity we show with an arrow because we show vectors with arrows, and velocity is a vector. It has a size and a direction. And so the arrows representing the overall velocity of any projectile is going to be made up of a series of components that together give us a resultant velocity, which is the diagonal velocity that we see at any given instant. That makes up the nice arc that we see when we go ahead and throw or launch projectiles. Okay, and so what we're looking at here is, as we solve these problems, we're going to focus on the vertical component, and then we're going to focus on the horizontal component. We like to simplify things in physics, take them one at a time, solve them that way, and life is a little bit easier. Okay, but why do we make that distinction? Well, it turns out that in two-dimensional motion, the horizontal component of our velocity does not change unless you have a very significant air resistance, and we like to find the theoretical maximums, so we tend to ignore air resistance. So for our problems, we're going to say the horizontal component of our two-dimensional motion does not change. That'd be like this ball rolling along the surface, whereas the vertical component of our two-dimensional motion is going to change. In fact, it's the exact same as a free fall problem that we've seen in the past. Why? Turns out vertical forces affect vertical motion, but vertical forces don't affect horizontal motion. Okay, so if they don't have a force, we're not going to have an acceleration, and acceleration is what causes our velocities to change. Okay, so that gives us the following. The horizontal component of motion for projectile is completely independent of the vertical component of motion. Each component is independent of the other, but their combined effects produce the curved paths that we see in our projectile motions. All right, if we were to look at the actual math behind it, the combined velocity vector that we'd call, say, the resultant vector of our vertical part and our horizontal part, we can get with a little bit of math. It turns out the overall velocity is equal to the horizontal velocity squared plus the vertical velocity squared, and that gives us the overall resultant velocity squared. Okay, let's take a look at this quick example. If we go ahead and throw an object upwards and its components are 30 meters per second vertically, 5 meters per second horizontally, after t equals 1 second, we're now at 20 meters per second horizontally. Remember, g is the acceleration due to gravity, negative 10 meters per second every second, so 10 meters per second squared. 1 second after that, we're at 10 meters per second. Then we're at negative 10 meters per second, negative 20 meters per second, negative 30 meters per second. These are the vertical components of our velocity. We said that the horizontal component does not change. If we have no air resistance, it doesn't change. So we have 5 meters per second. At the peak, our horizontal velocity is 5 meters per second. Our vertical is 0 meters per second. Okay. 5 meters per second. Horizontal velocity doesn't change. We have no horizontal forces acting on our object, so we have no acceleration. If we want to find the resultant velocity, the overall velocity, right? The diagonal that we see when we actually go ahead and see a real motion, because our overall objects don't travel like that, right? They travel in a nice arc, so our resultant velocity is our diagonal. Okay, let's try and calculate it here. So we have resultant squared is equal to our horizontal squared plus our vertical squared. So we have 25 plus 100. So this is the square root of 125. Okay, Same thing down here. We have 20 squared, so 20 squared becomes 400 plus 25, so this is the square root of 425 meters per second. Then we have the square root of 925 meters per second. Okay, how did I get those? I used this equation right here. All right, what if we launched an object completely horizontally? We didn't go ahead and throw an object upwards at an angle, which is what we typically think of when we talk about projectile motion. But we define projectile motion as any two-dimensional motion, okay? And so step one, before we solve the hard problems, let's just look at a simple, we launched an object off of a table with an initial horizontal velocity. Okay, reminder that the x component does not change, the y, the vertical component of our velocity, just acts like an object in free fall. Okay, so we have three different balls here, all launched with a different horizontal velocity. We'll say the one to the very left has the lowest horizontal velocity. The one to the very right has the greatest, so let's go ahead and draw those. All right, we're drawing with the longest arrows because it is the greatest horizontal velocity. Our horizontal velocity doesn't change through the overall motion because we have no force acting on it horizontally. Our vertical forces, though, it's a different story. 1 second, at t equals 1 second, we have 10 meters per second of vertical velocity. It's all the same for all of these, regardless of their horizontal velocity. They're completely separate. Okay, and we treat the vertical velocities like a free fall problem. So at t equals 1 second, t equals 2 seconds, t equals 3 seconds, t equals 4 seconds, we have our vertical velocity is equal to negative 10 meters per second. That applies to all of these guys. At t equals 2, we're at negative 20 meters per second. T equals 3, we're at negative 30 meters per second. And t equals 4, we're at negative 40 meters per second. Why? Because we have the acceleration due to gravity, which is 10 meters per second. Per second, that's our change in velocity for vertical motion. Okay? Let's take it a step further. So we actually care mostly about finding where our projectile is going to land, right? That's the more interesting question. In order to do that, really what we do is we just apply our kinematic equations. We recognize again that the horizontal velocity of a two-dimensional projectile does not change unless you have a whole lot of air resistance, a big horizontal force, which we're going to say doesn't happen, so this is generally true. The y, the vertical velocity, acts like an object in free fall. All right, so our steps to solve these sorts of problems: apply our kinematic equations, solve for the time it takes to hit the ground, find the horizontal displacement. All right, so step one, let's apply our kinematic equations. We had a 6-step process we talked about previously, but it boils down to what are you given, what are you trying to find, and solve. So reading this, we have a cannon is shot a projectile off of a 40-meter cliff at 100 meters per second. Find the time to hit the ground and the location that the cannonball lands. All right, so let's just draw a picture. Our ball shot horizontally. Eventually it hits the ground. We want to find this distance, delta x. We also want to find the time to fall. Okay. Step 2, let's go ahead and write out our known values. We have our horizontal velocity is 100 meters per second. Our delta y, our displacement in the y direction, is 40 meters. Okay. And so good practice is to write out sort of the horizontal and vertical and solve them separately, and take the time from the vertical and plug it in over here. So we want to find the delta t that it takes to fall this distance. Well, let's look at our equations. We don't have an initial vertical velocity. We have an acceleration. We have time. So we say, or we're finding time, and we have a delta y, a change in position. All right, so we say delta t is equal to 2 delta x divided by g, and the square root of all of that. We go ahead and we plug in. So we have 2 times 40 divided by 10. So we get 80, the square root of 80. The square root of 80 divided by 10, so square root of 8. All right, horizontal, we want to find displacement. This looks like a good equation up here. We have our let's see. Horizontal velocity is the same, so we're actually going to use a modified version of this. We're going to use delta x equals 1. So we can use this one. It's the same equation. Because it's got the 1/2, it's the same equation as this. All right. The addition of this 1/2 allows us to say that that's the case. So we have delta x equals 100 meters per second times our time, which is the square root of 8 seconds. Seconds cancel. And so we have 100 times the square root of 8. That's the overall horizontal distance that our object travels. All right, we follow the procedure, apply our kinematic equations, solve for the time it takes to hit the ground, find the horizontal displacement. All right, let's do one more. A ball is launched off of a 45-meter high cliff with an initial velocity of 6 meters per second. How long is the ball in the air for? How far will it go? What will be the final speed and direction? All right, we're going to solve A first. So how long is the ball in the air for? We're going to skip some steps in the interest of time, but we have our displacement vertically is 45 meters. Our initial horizontal velocity, which is going to be the horizontal velocity throughout, because it doesn't change, is 6 meters per second. With this equation right here, we have A is equal to negative 10 meters per second squared. So we go ahead and we say delta t is equal to the square root of 2 delta y over acceleration. So we get 90 divided by 10 square root of that. So 3 seconds. All right, how far will it go? Delta x equals our horizontal velocity times our time. So we get 6 meters per second times 3 seconds, and we get 18 meters. So this object will go a total of 18 meters. How did we get that? Step 1, find the time from the vertical motion. Step 2, apply that to our equation, delta x equals vx times t. Okay. This one, we're going to skip for now in the interest of time. Let's just look at our summary. All right, so we have projectile motion is separated into a horizontal and vertical component. The horizontal x component of our velocity does not change. The vertical component y does change because we have gravity, a force constantly acting on it. And it's the same as a free-falling object. In order to solve a horizontal motion problem, we go ahead and we find the delta t, the time to fall, and then we plug that into our equation down here and say the overall horizontal distance is going to be equal to the horizontal velocity times the time it was in the air. We get this one from vertical motion, and this one down here is our horizontal motion. All right, that's it for now. We'll see you guys back in class. Good job.